talk on fundamental physics and provided me opportunity to meet with this wonderful audience. Let's start from this point that if you take a quick look of your surrounding, you see different objects like the chairs you are sitting on, the wall of this room, the desk, our bodies, and the picture of this ice cube which I'm showing in the slide. All these objects are made of a stuff which is called matter. And this stuff has a fundamental property which is called mass. Now, ever since the dawn of civilization on Earth, humans have always been fascinated by hundreds of thousands of different forms in which this matter exists and the concept of its true nature. And the book which we have selected, that is, I'm sorry to have this distraction. The book that we have selected is actually an account of human understanding of matter as evolved over the centuries and shaped by diverse philosophical inquiries, scientific discoveries, and technological advancements. The authors invite us to begin with something which we can observe with unaided senses and ponder on the nature of matter without having the facility of physics lab or a particle physics collider. In order to facilitate us, to free us from the effect of modern scientific education, the author imagined a Greek philosopher strolling on a beach on a sunny day somewhere in 5th century BC. He is preoccupied with one fundamental question: what is the world made of and how it put it together? So he looked around, he see many objects like the sandy beach, blue sky with scattered clouds, distant hill, a flock of sheep, and the restless sea. But he doesn't see any gods. Although his daily life and the rituals are governed by a principle that he has to pay respect to the gods, but today he decides that he will find the answer of this fundamental question irrespective of his belief or prejudice. So setting aside his prejudice and his superstitions, you know that it is a common observation that miracles do not happen in everyday life. It doesn't happen that things just disappear to nothing. Surely they fade away, they transform, but they do it slowly. It just do not happen that things just disappear. So therefore, he makes his first conjecture that nothing goes to nothing. And the corollary of this conjecture is that nothing can come out of nothing. Though having set his premises, the first premises, he think of a thought experiment. Imagine that you have a piece of paper and you divide into the two parts. And then you divide each part into the two parts, and then each part further into the two parts. And imagine that what would happen if you keep on doing it endlessly. So what would happen? You end up dividing it to the nothing. So this thought experiments imply that a piece of paper can be transformed into the nothing by infinitely dividing into the parts. Contrary to his initial conjecture that nothing can go into the nothing. So therefore he concludes that matter cannot be divided infinitesimally. There is a small, indivisible part of the atom which is called atom. Atom is, is a Greek word which literally means something which is indivisible. Now, by definition of atom, the atom must be moving in something which he called white, mean nothing. And then he speculates that atoms come in different shapes and different forms of matter are composed of mixture of different types of atoms with different proportions of hard atoms and white. Historically speaking, that there were actually a handful of Greek philosophers which were thinking on these lines. The first of them in this line was Leucippus, who actually conceived the idea of an atom in 5th century BC. Democritus, who developed the atomic theory further, introducing the concept of shape, size, and weight of atoms moving endlessly in white. And then we have Epicurus, who articulated and documented several summaries on the Democritus atomic theory. And we have Lucretius, who gave it a poetic expression by writing an epic poem, the Rerum Natura, on the nature of things. But Aristotle and most of the Greek philosophers were actually against the atomic theory. They were rejecting the idea that atom and white exist. Although Aristotle believes that matter can exist in 4 different forms: earth, water, air, and fire. But it is continuous in its nature. Now, after covering the Greek thoughts, the author quickly takes us to the 17th century. Assuming that nothing significant happened in the medieval period, where the philosopher's attention was absorbed in reconciling the ancient Greek philosophies with theologies. And that was the reason that the natural philosophy, which was a separate discipline in the time of Greeks, that become inextricably entangled with the theological questions. And Aristotle's pronouncements on the nature of matter, his earth-centered cosmological model based on perfect circular motion, enshrined in Christian religious orthodoxy. But eventually, things started to get free, initially because of the monasteries, which later turned into the universities. And very slowly, it is possible to think or speculate on the lines which are no more religious in nature. And thanks to the philosophers of 17th to 18th century, which are broadly categorized into 2 groups: mechanical philosophers, in which we have Galileo, Kepler, Boyle, Hines, and Newton, and classical modern philosophers. Mechanical philosophers were actually engaged in gaining the knowledge of physical world by applying observations, calculations, and reasons. Whereas classical modern philosophers, they were debating the extent to which we can gain the knowledge of the physical world by merely applying reason and observation. But most of these mechanical philosophers, they held a general understanding of atomic theory, but their version of atomic theory was in nowhere more sophisticated than the Greeks' atomic theory. However, Newton made a small contribution. He thought, rather I would say he speculated, that it's true that these tiny billiard balls are moving in the white, but they are also interacting with some sort of force other than the force of gravity. But his idea was purely speculative. He has no experimental evidence to support that atoms are interacting through some forces other than the force of gravity. And then it took us one after the Newton, which we usually regard as the first scientist in the new generation of scientists. It took us 100 years to actually provide an evidence for the existence of matter. matter, and that did not come from the physics, it came from chemistry. By the end of the 18th century, the chemists were able to make a clear distinction between what we call elements, compounds, and the mixtures. And Louis Proust, first of all, identified that elements are always combined in a fixed ratio to form a compound. For example, if you have 1 gram of hydrogen and combine it with precisely 8 gram of oxygen, all turns into the water. So the ratio of hydrogen to the oxygen is 1 to 8. And similarly, if you combine 1 gram of hydrogen with 4 gram of oxygen, you can produce oxygenated water. This is actually the old name of hydrogen peroxide. And similarly, it holds for carbonic acid gas and carbonic oxide gas, which are old name of carbon dioxide and carbon monoxide. And then after a few years, Dalton found that when same two elements form two different compounds, the ratio of the masses of one element to a fixed mass of the other element will always be a whole number. And this is something which you can observe in these values as well. Now, on the basis of these two laws, Dalton formulated atomic theory, which is called Dalton theory, which based on these assumptions, and these assumptions are justified by the observations, that all matter is composed of tiny, indivisible particles called atoms, and all atoms of given elements are identical in masses and properties. Atom combines in simple whole number ratios to form compound, and chemical reactions involve the rearrangement of atoms. So it took us about more than 2,000 years to actually prove or provide some empirical evidence in support of the existence of matter. Now, it's an irony that after 100 years more, when the chemists fully gripped the idea of atom, the physicists were trying to break it. And it began with J.J. Thomson, who through his famous discharge tube experiment showed that atoms contain negatively charged particles, which we call electrons. So this arose a question that since atom is on the whole electrically neutral, so therefore there must be some compensating positive charge. And the question is that how the electrons and the compensating positive charge is distributed in the atom. Thomson speculated, there was no experimental evidence to support it. He assumed that atom is a positively charged paste in which the electrons are embedded. And later, after about a decade, Rutherford, through his famous Rutherford scattering experiment, in which we fire high-energy alpha particles with a thin gold nucleus, foil of nucleus, he found that atoms' electrons are not embedded in a positively charged phase. Rather, they are revolving about it. And in this way, he found that there is a central region in the atom where all of its positive charge and the bulk of mass is concentrated. This central region of the atom is called nucleus. And then it was found that the nucleus is itself made of two more fundamental particles, which are called protons and neutrons. And then in 1960s and 70s, there were some experiments which were performed in Stanford Linear Particle Accelerator, which show that there is another layer of structure inside proton and neutron. They find some more fundamental particles inside protons and neutrons, which are called quarks. So today we know that a proton is a bound state of two up quark and one down quark, whereas a neutron is a bound state of two down quark and one up quark. Now, having covered this history, let's go back to the ice cube and let's ask the same two fundamental questions: that what is it made of, And where will we find its mass? Now we have a definite answer. It is made of water molecules, and each water molecule is made of 2 hydrogen atoms, 1 oxygen atom, and each atom is made of electrons and nucleus, and each nucleus is made of protons and neutrons, and protons and neutrons are made of quarks. So far, we go that far only. And where we have to find the mass? Now, its answer seems to be obvious. The mass of the ice cube is coming from the mass of atoms. But from where the mass of atom is coming? The mass of the atom is coming from the mass of electron, which is very small. The bulk of the mass of the atom is coming from its nucleus. And the mass of the nucleus is coming from the mass of proton and neutrons. And mass of the proton and neutron is coming from the quarks. So this is the answer of these 2 fundamental questions. It is remarkable that after about 23 or 2400 years, we have conceptually arrived at exactly the same answer which thousands of years, hundreds of thousands of years, Greek philosophers thought about. There are some indivisible building blocks of the matter or the building blocks of the universe. It is remarkable that everything in this room and outside is merely a different arrangement of 3 fundamental particles: electron, up quark, and down quark. That includes our bodies as well. My body is also just a different arrangement of same 3 fundamental particles. It is remarkable, but there is a problem. And the problem is that it's a lie. It's a lie which, when we say that the universe is made of some fundamental particles, the real building blocks of the universe are not particles. Something which are far more abstract, far more nebulous. These are what we call quantum fields. The building blocks of the universe are not the particles, they are actually the quantum fields. So if you are a believer, then you should say that when God created this universe, God didn't create any particle. God just created certain quantum fields. And everything emerged from these quantum fields. So why it is so? Why the building blocks of the universe are not particles? They are fields. But actually, when we observe the universe, we see the particles. So we have to answer this question that how the particles emerge from the quantum fields. And we also have to answer this question that why we believe that the real building blocks of the universe are not particles, but the quantum fields. I can give you a simple answers of these questions. But first we have to understand that what are the quantum fields. By definition, quantum field is a field which is governed by the laws of quantum physics. So maybe I should say a few words about the field and then a few words about the quantum physics. What is a field? This is not, by the way, field. What is a field? A field is a quantity which is defined by specifying its value at each point of space. Let me give an example. Think of the temperature of this room. If you have to define the temperature of this room, what you will do? You will bring a thermometer, place it somewhere, and you would say, this is the temperature of the room. No, this is not the temperature of this room. This is the temperature of the point where you have placed this thermometer. At different points of the room, you may have a different temperature. So if you have to really define the temperature of the room, you have to specify its value at each point of space. And that makes this concept a field, because a field is something which is defined by its value at each point of space. Similarly, those who have studied the physics, they know electric and magnetic fields are also the fields. Or if you just drop some sugar in in the cup of tea, then the oscillations which occur at the surface, they also as the field, because they are defined by its amplitude at each point of the surface. And then we come to the quantum physics. There are two important and salient features of quantum physics which we have to understand. First of all, quantum physics implies that a system can have only certain discrete values of energy. Think of the atom. Electron in the atom can exist only certain discrete values of energy. So this is the first characteristic of quantum system. And the second is that there's a fundamental limit with which we can measure a physical quantity. Classical physics tell us that you can measure a physical quantity with any precision, whatever you like, that is fixed by the precision of your instrument. But quantum physics tell us that no matter how precise instrument you construct, there is a fundamental limit which you cannot cross. And this is actually dictated by one of the uncertainty principles which you have studied at your FSC level, which is called Heisenberg uncertainty principle. So when you suppose that the field is governed by the laws of quantum physics, then first of all it happens that the field can have only certain discrete values of energy. And it turns out that these discrete values of energy are equally spaced. And the spacing between any two levels is called the quanta, or the packet of energy. And it turns out that these quanta, or the packets of energy, has exactly the same property as that of a particle. Those who have studied physics, they actually already know that photon is a quanta of electromagnetic field. So what we are trying to say is that it is not only the photon which is a quanta of a field. What we are trying to say is that every particle in the universe is a quanta of some field. For example, think of electron. So all the electrons in this universe are the quanta of single field permeated in the whole universe, which you can call as electron field. So if there are three fundamental particles, electron, up quark, and down quark, so what we are trying to say that there are actually three fundamental fields: electron field, up quark field, and the down quark fields. Okay, the next question is that why we believe that the particles, that the fields are more fundamental than the particles. There are actually two reasons for this which I would like to give here. First of all, we find that these fundamental particles, which are the quanta of the fields, they have some magical properties. A particle can transform into another particle. So down quark instantaneously can transform into the up quark, and up quark can instantaneously transform into the down quark. It's not that the down quark already contains up quark. It can't be true, because if down quark contains the up quark, then up quark cannot contain the down quark. So down quark just transform into another particle. It's a magic. It's like that I instantaneously transform into Dr. Smiley. This is the magic. But this magic is happening at the fundamental level. And this can only be explained if we suppose that these are not the particles, these are the quanta of a field. Because field can transfer energy into each other. When a field will transfer energy into another field, some of the quanta of the first field will disappear and they will reappear in the form of the quanta of the other field. And I would like to give you one more evidence, because when you learn something new which is challenging your common observation, it is very hard to learn it. So that's why I would like to give you one more evidence that why we believe that quantum fields are the real building blocks of the universe. I show you a picture. And you wouldn't believe me that when I would say that this is the picture of an empty box. A box from from which everything has been removed. Now, if particles are the most fundamental entity or the real building blocks of the universe, and if you remove them from the box, nothing should have left in the box. But this picture shows us that that's not true. Something still left there. What you are seeing here, these are actually the quantum fluctuations. You know, because of the Heisenberg uncertainty principle, the absolute state of rest is not possible. Because when you say the particle is at rest, its position is precisely fixed, and its momentum or velocity is also precisely fixed, which violate the Heisenberg uncertainty principle. So what happens is the field has to always oscillate to protect Heisenberg uncertainty principle. So this actually picture shows that when you remove the particles from a box, what you actually remove is the energy from the box. That brings the field in its ground state. You can remove the energy from the box, but you cannot remove the field itself because it's everywhere in the universe. So when we remove all the particles from the box, the field goes into the ground state, but because of the Heisenberg uncertainty principle, the field is still fluctuating, and what you are seeing in this empty box are the quantum fluctuations, which proves that the real building blocks of the universe are not the particles, but field. So the question is not this, that what are the fundamental particles in this universe? The question is that what are the fundamental fields in the universe? So far we have found the field of U quark, up quark, down quark, electron quark, and there is another field which is producing the neutrinos. And there is another generation of fields, which are collectively called the matter fields. They interact through another set of fields and produce the interactions between them. And these are the fields which we have discovered in this universe. So these fields, they are interacting with certain forces, including gravity, electromagnetic interaction, strong interaction, and weak interaction. And the laws of interaction, which you can consider as the most fundamental laws of physics, they are given in this equation. I do not expect you to understand this equation, but you can actually just appreciate that this is the pinnacle of our understanding of the physical world around us. With this equation, and if you just write on a page of paper, it takes 2 lines to write it. But with this 2-line equation, you can explain everything which is happening in this universe, starting from Big Bang to right now. Apart from a couple of facts, that's why we are still developing this equation. We believe that it is not complete. So if you look at it carefully, you see in this equation, which represents the fundamental laws of physics, there's something which is missing. And you see there's no m in this equation. There is no m. Literally there is no m in this equation. M stands for mass. So what does it means that the quanta of the fundamental fields in the universe are massless, but they are not massless. Most of them have some mass. From where they get the mass? And why we suppose that they are massless? Actually, this equation is constructed by imposing certain symmetry which we have observed in the nature. And the consequence of this symmetry is that we can't put masses in this equation, because if you put the masses in the equation, the very symmetry from which you have constructed this equation, that would be broken. So that's why when the physicists constructed this equation, there was no mass term. But there are some particles have the masses. So they invented or they discovered a mechanism, mass generating mechanism, which is called the Higgs mechanism. And what exactly is this mechanism? I can't explain it in detail because the theoretical physicists which works in the quantum fields, they are very good in physics and mathematics, but they are very bad when they actually have to explain these ideas to the ordinary people. No one can explain it. It's just a rough understanding of how the particles get the mass. So what we have supposed that there exists a field which is called Higgs field, and this field is permeating the whole universe, and the particles get mass when they interact with the Higgs field. The greater the interaction, the greater the mass which we have. And if Higgs field really exists and it produces the masses, so we should be able to observe the Higgs particle, the quanta of the Higgs field. The particle physicists did find this quanta in 2012 in Large Hadron Collider, which was actually built for this purpose to discover this particle which gives masses to all the other particles. So this implies that mass is not an intrinsic property of matter. The particles of the matter, which are the quanta of the field, they acquire it through something which we call the Higgs mechanism. But it doesn't complete our story. We have one more riddle to cross. If you look at the proton and neutron, and I'm putting focus on these particles because the bulk of the mass of an atom is due to the nucleus, and the nucleus is made of protons and neutrons. We see that the mass of up and down quark is about 3 MeV. So therefore, the mass of a proton should be about 10 MeV. MeV is just a smaller unit of mass. But when we actually measure its mass, it is not 10 MeV, it is about 1000 MeV. So where this 99% of the mass of the proton and neutron is coming from? And this is explained by another phenomenon. So if you go inside the proton, you see the quarks, and these quarks are interacting with each other with a force which is called strong force, which is mediated by particles which are called gluons. And it turns out that inside the protons, these gluons are extremely sticky. They stick with the protons and effectively increasing their mass from 3 to 300 MeV. Actually, they produce a shift in the energy from 3 to 300 MeV. And thanks to the Einstein's equation, that mass is the measure of the energy. So because of the shift in the energy which is produced by the gluons, we are getting the bulk of the mass of the proton. So only 1% of the mass of the proton and neutron is actually coming from the Higgs mechanism. And 99% is coming from the stickiness of otherwise massless gluons. So let's come back to the ice cube once more time, and perhaps last time. What is it made of? Previously we said it's made of electron up and down quark. I would still say that it is made of electron up quark and down quark, which are the quanta of 3 fundamental fields in the universe. And what is mass? Mass is not an intrinsic property of a material substance. It is not something what matter has. It is the behavior of quantum field. It is something which they do. So next time when you climb up over a scale, ask yourself a question. What am I measuring? And if you have followed some parts of this talk or later on the book as well, the answer is remarkable. 1% of what you are measuring is coming from the interaction of up, down, and electrons of your body with the Higgs field. And 99% is coming from the energy content of otherwise massless gluons dancing back and forth between the quarks locked inside the protons and neutrons of your body. And this is the mass, and this is our journey from Greek atoms to the quantum fields. Thank you very much.
Thank you so much, sir. मेरा हालांकि फिजिक्स वाकई बहुत ड्राई थी, लेकिन जितनी इंटरेस्टिंग आपने कर दी ना, उसके बाद मेरा दिल करता है काश मैंने फिजिक्स लिया।
very nice talk. I'm assistant professor from a computer engineering department from University Lahore, and I got this book written around 3.5 years ago, and I have read this book. So that's why I came here to listen to this talk, but it was very interesting. The question is, you showed a slide of the beta decay. Can you please be open?
Of course. Beta decay. It's a radioactive decay process. Yeah, this one is right.
I think so. The dice is making hurting in front of me. The lower process is actually beta positive decay, if I'm not wrong.
Yes, it's
It's a beta positive decay. It's emitting the positrons.
Yes, it should be positive.
But the question is, it is highly probable that beta negative decay occurs frequently in the radioactivity. But the beta positive decay is less frequent.
That's not true.
And that's what I want to ask. The free neutron decays around 10 to 15 minutes. But the free
yes, that's a different story.
Proton does not.
Yes, if you talk about a free neutron, it can disintegrate into the proton through beta minus decay.
Yes.
Right? But a free proton cannot decay into
This is the question.
Yes, but inside the nucleus, it's possible that they could decay. Is it your question that why they decay inside the nucleus?
I also
To some extent, in addition to this, that why these two processes are not equally processed, why the beta minus is frequently occurs.
Can you
Okay,
please,
I reply to you.
Sure.
Yes.
can you please shift the conversation to some human language, please?
It's very difficult, and I give you the reason. That the language of physics, the language I would say the nature, is not the human language. It is the language of mathematics. Our human language has been evolved by the experience of everyday life. You can explain in our human language what you see.
But we
But
do
what
have.
you see in the Large Hadron Collider, that cannot be explained.
But then the point is that we do have scientists all over the world who make it palatable for common people like us.
Yes.
So it's just that through analogies, since I come from literature department, so many, for instance, scholars like Neil deGrasse Tyson, and then presenters like Jim Al-Khalili, and then we have Professor Brian Cox, and most famously Carl Sagan. So all these scientists have actually made it digestible for ordinary human beings like us. So it was just a humble suggestion.
Actually, we have to do it. We have to do it. Because if we will not be doing it, and let me remind you an incident. Do we have 1 moment?
Yes.
When the Large Hadron Collider was being constructed, the United Kingdom, I think that at that time it was John Major who was the Prime Minister, and it was a personality. And the United Kingdom pledged 50 million for the construction of Large Hadron Collider, and it was his science minister who was supposed to release this grant. So he was told that there is a big collider, Large Hadron Collider, which we have to construct, and you have to pay 50 million pounds for this. He said that why we have built this collider. Physicists told him that we want to discover a particle. This is the last missing piece of a jigsaw puzzle, which is called the Standard Model. It's extremely important to discover it, but he was unable to understand it. He said to all the scientists that write a one-page presentation, and I will choose the best 5 countries and will give them the bottle of champagne. And the best entry was chosen. And you know how he explained the Higgs mechanism? He used the language of politics to explain it. He said that think of a cocktail party of going on of a conservative party, and the Margaret Thatcher, you know, that was a celebrity, enters in. So everyone will rush in. And as she will move, some people will go away and some will also be scattered. And all the time, she will always be scattered by a certain number of humans that will impede her motion, and that's how she will get the mass.
This is the last question for this session.
Yeah. Hi, Professor. I'm just curious about physical dimensions of life. I mean, the bodies of living organisms are composed of fields, cells, atoms, And I are listening that how these lifeless fundamental particles or fields come and join harmoniously to give, any life into being, and how life comes into being. So I just want to ask about what is the role of nature, and that's fine.
I think we should discuss it later on.
Thank you, sir. Thank you